This is a video on waves. The first thing we want to think about is, what is a wave? There's one type of wave which you've all seen. That's a water wave. What does it look like? Yes, it goes up and down and up and down and up and down. Consider a particle on that water wave. The water wave is moving to the right. You can see it's moved that way. That particle there, what's that particle doing? Is it moving to the right, or is it moving up and down? A lot of students got this wrong. That particle there is not moving to the right. The water particles stay where they are, otherwise you'd see water lakes all bunching up to one side of the lake as all the water moved along with the wave. No, the water stays in the pond. Each particular particle is going up and down and up and down, and it's just moving up and down. And the next one is also moving up and down. Trough. That's the first vocabulary I want you to learn. Trough and peak. That's the top and the bottom of the waves. The next vocabulary I want you to learn is frequency and wavelength. Frequency is the number of waves that pass a point. Say I'm looking here. That's my eye looking. How many waves pass my eye, pass a point per second? Wavelength is the distance from peak to peak or from trough to trough. The only equation I'm expecting you to know is that frequency times wavelength equals the speed of the wave. And the symbols we use are F for frequency, lambda for wavelength. F is measured in hertz, that's number of oscillations per second, and lambda is measured in meters. Two other words you may come across are period and amplitude. The period is the time it takes for a wave to do one vibration, each part of the wave to do one vibration. So it's going to be in seconds, and that particle will take so many seconds to go up, down and back up, back to the same point. The amplitude is the distance from the rest position, where the water would be if there was no wave, to the peak, or it's the distance from the rest position to the trough. Therefore, it's half the distance from the peak to the trough. There are two types of wave. There are longitudinal waves and transverse waves. What is the difference? In the transverse wave, the particles move at right angles to the direction of movement of the wave. You can see that in this video. In a longitudinal wave, the vibration is in the same direction as the wave moves. The particles move in the same direction as the movement of the wave. Water waves are actually a combination of longitudinal and transverse waves. Sound is a good example of a longitudinal wave. In sound, First, there's always something vibrating. If you put your hand on your voice box while you speak, what do you feel while you're speaking? Vibrations. There's always something, some sort of drum that vibrates, and this pushes the air and squishes it together, and that compression moves through the air as a wave. The particles of the air, as you can see, are moving in the same direction horizontally as the direction of the wave. So sound is a very good example of a longitudinal wave. To demonstrate frequencies, I'm going to twang this ruler. When it's long, it should move slowly, and when it's short, it should move fast. Slowly, fast. Can you hear the difference in the sounds? A slow frequency is a deep note, and a fast frequency is a high note. Low pitch, slower than when you make a high pitch. Frequency of sound determines its pitch. Using the same experiment, I should be able to show you what a difference amplitude makes. Let's try a small amplitude, and now let's make a big amplitude. Small, big. As you can see, the amplitude of a sound controls its loudness. Small amplitude sounds are quiet, and large amplitude sounds are loud. A good example of a transverse wave is light. Light, the posh science word, is actually the electromagnetic spectrum, because visible light is just the bit of it we can see. There's a lot more to it than that. But light is made up of an electric field and a magnetic field. Electric fields are fields which push charges, say that's negatively charged. An electric field, if it's negative here, will push that negatively charged electron away. If it's a positive voltage there, then that electron will be attracted. A magnetic field is a magnet, which, as you know, will push another magnet away if they're the same, pull it if they're opposite. What light is actually, it's an electric field that goes up, positive, then negative, then positive, then negative. So if I put a little charged particle there, it would be attracted up then down, up then down, up then down. And at right angles to this, there's a magnetic field which will act like a magnet. And this time, if I put a magnet there, it'll push the magnet in and out, in and out. This is a transverse wave because the wave is moving, say, to the right, but the magnetic field and the electric fields, which are at right angles to each other, are moving up and down, not to the right. So the electromagnetic spectrum is a very good example of a transverse wave. And the electric field and the magnetic field are at right angles. The frequency of like a million, that's the light we can see in our eyes. It vibrates a million times a second. Light can be strong enough to knock an electron out of an atom and leave it positively charged. A charged particle is called an ion, so light can ionize. It can make atoms charged, but only if it's got enough energy. Everything is both waves and particles, and the electromagnetic spectrum is not only made of waves, but these waves are concentrated in little packets, quanta, little bits, called photons. And the energy of a photon is given by Planck's constant times the frequency of the photon. So it's the high energy, i.e. high frequency photons, which are most ionizing. I use this ionizing property of electromagnetic radiation to remember all my parts of the electromagnetic spectrum. I always start off with visible, because visible light is the light we see, and that's got a wavelength of about 10 to the minus 7 meters and a frequency of about 10 to the 15 per second. Per second is hertz. The units of frequency are hertz. Visible light is all the colours of the rainbow, from red to blue. Then I try to remember what's on either side of red and blue. They're going to be colours that we can't see. Colours which are similar to red and blue. Well, red is similar to infrared, and blue is similar to ultraviolet. Now, here's where I remember ultraviolet causes tanning, but it also causes cancer. It's ionizing. So this way must be increasing energy. Energy, if you remember, well, energy. And energy was HF, so it's also frequency. So we know frequency is going up that way. To complete the dangerous side, the side that's highly ionizing and will probably kill your cells, I just think of dangerous rays. We've got X-rays and gamma rays, which we know are highly ionizing and dangerous. If gamma rays have more energy than visible light, then we know the frequency must increase. So the frequency there for visible light was 10 to the 15. The frequency for gamma rays is more, it starts at about 10 to the 20. So the frequency has gone up, and the wavelength is about 10 to the minus 12 meters. Anything with a wavelength smaller than about 10 to the minus 12 meters is a gamma ray, and anything with a frequency higher than about 10 to the 20 hertz is a gamma ray. So gammas start there. To the other side of the spectrum, this side should not be so dangerous. Infrared is just heat radiation. Hot things give it off. Not so dangerous, I suppose you could get warm. Next to it is microwave. Now microwave's a funny one. As I say, this side shouldn't be dangerous because the photons are low energy, low frequency. But the funny thing about microwave, it is just the right frequency to vibrate a hydrogen nucleus. And so it's just the right frequency to vibrate water. And vibration is heat, so basically it heats up water. So microwave is incredibly useful for heating up anything that contains water. Then what is not dangerous at all? It's everywhere, and it's got a really long wavelength and not at all dangerous. Last would be radio. That has a wavelength of more than about a meter and a frequency of less than about 10 to the 8 hertz. If you remember Earlier we had the equation speed is equal to frequency times wavelength. So if we times any of these together, we find the speed of light is about 10 to the 8 meters per second. I think that's right. 20 minus 12, that's 8. 15 minus 7 is 8. 8 minus 0 is 8. Yes. So we know that the speed of all electromagnetic radiation in a vacuum is about 10 to the 8 meters per second. In fact, the speed of all electromagnetic radiation in a vacuum is 3 times 10 to the 8 meters per second. So that's all the parts of the electromagnetic spectrum. Now let's go on to uses for different parts of the spectrum. Gamma rays are really high energy, so we can use those to kill cells. So we can use those in medical treatments, medical therapy for things like cancer. X-rays, it'll penetrate through most matter unless it's got a really high atomic number. So we can use that to see through the body, X-rays. UV, oh, that's for tanning. I think we also make vitamin D out of it. The visible light, we use that to see, to take photographs. Infrared, infrared cameras. Microwave, isn't that mobile phones? Yes, I do believe we've had a lot of people complaining that mobile phones may not be safe because they use microwave. Radio is obviously used in radio and TV. Now I'd like to talk about 4 phenomena of waves in general. Reflection is something you already know from looking in the mirror. It's that waves will bounce off flat surfaces. 3 times 10 to the power 8 meters per second is the speed of light in a vacuum. If it has to go through a material, it will be slowed down as it collides with the atoms of that material. Because light slows down as it enters a more dense medium, it looks like it bends. Different frequencies are different colours. So red is a different frequency light to blue. Each frequency is a different colour of the rainbow. You already know which is more frequency, red or blue. You can work it out by which is more dangerous for you. Blue is next to ultraviolet, which causes sunburn. So blue's more dangerous. So blue's got the higher frequency. That means its photons have more energy, so it interacts more with atoms as it passes through them. So it loses a lot of energy as it passes through a material, much more than red. So blue light slows down more as it passes through a material than red light does. This means that blue light bends more as it passes through a more dense material than red light. And you can see this in a prism, because you'll see the blue light as it passes through the prism bends more, and so we can use a prism to separate out the colours. And you'll see blue being bent more than red, which is coming sort of straight through the prism. This bending of light as it goes from one medium to another is called refraction. Another property of waves is interference, which is when one wave goes on top of another wave, they'll add together, or if one's a trough and the other one's a crest, they'll take away. This is called superposition, when one wave adds to another, and it gives rise to interference patterns. Diffraction is the last thing I want to talk about. This is a phenomenon where waves behave quite differently to particles. If you throw particles through a hole, they go in a straight line through the hole. But unlike particles, waves, when they go through a hole, they spread out, they curve. So you get curved edges and they can go round corners. This is why you can hear round corners. Light does it too, it will spread out from a point. This phenomenon is called diffraction. And we can get interesting interference patterns from using 2 diffraction slits or more. Diffraction, refraction, interference and reflection are really properties of waves in general, not just electromagnetic waves, but obviously electromagnetic waves are waves, so it's true for them as well. Sound travels faster in a denser medium, faster in a solid than a liquid, faster in a liquid than a gas, while light slows down in more dense mediums. This is because sound requires a medium in which to travel, such as a gas, liquid or solid. This is why there can be no sound in outer space, because it's a vacuum. Sound is a pressure wave which causes the molecules in the air, for example, to oscillate. This oscillation is propagated through the medium of the matter. Since a medium is required for sound to propagate, the closer the molecules are in that medium to each other, the faster the sound will travel. Light does not require a medium. What light is oscillating electric and magnetic fields. In space, they're free to travel at their maximum velocity of 3 × 10⁸ meters per second. When light travels through a material, it depends on the material, how much light gets through. For example, some materials are opaque, don't let any light through at all. So they travel slower as they travel through a material because they interact with the atoms.